All right, so for this session, we're going to be talking more in detail about how to run RMG jobs. I'm Sevi Harris. I just want to thank Yenting for the earlier version of these slides. If anything is wrong in these slides, it's my fault, not hers. All right, so as we saw from our last session, the general syntax for running RMG is you give it Python and then the path to your rmg.py script. You can add some extra options in there, and then you give it the path to your input file. So this is a very important concept for our PowerShell, or not PowerShell, terminal, is giving the correct paths. We'll go through a demonstration in a few minutes. One other thing you can do is add, there's this path environment variable, which you can use to tell your computer where to look for things. And so if you don't want to have to type out the long path to this RMG py thing every time, then you can add this line to your bash rc, which is not, you can run it once, or there's a file called .bashrc, which has a lot of configuration options and can be really helpful for configuring your environment. By default, all of your output files will end up being generated in the same directory as your input file. Okay, so one quick note, this might be a little outdated, but you want to make sure that when you're running RMG, if you're using Conda, that you want this, it shouldn't say base, it should say RMG env, and you can get there by doing Conda activate RMG environment. By default, your Docker will automatically put you in the right environment, but if you're using the developer version, you have to make sure that you activate your environment. There was an old style of Conda where you had to do source activate, but hopefully that's so far in the past that nobody has to worry about that. Okay, so what are some of the extra arguments you can give? We already saw the -h to get all of the different help options listed for RMG py. One that I use quite frequently is the -t, so that gives you a wall time. So what is the maximum amount of time that you'll allow RMG to run? I use this sometimes just for consistency. If I'm running RMG a lot of times, maybe with different libraries or different input files, but I want to sort of be fair and let RMG have sort of equal compute time each time, this can be helpful for getting your runs consistent. Although you do have to make sure that it's not cut too short so that you're getting the truncation error. And then there is also a parallelization option, the -n for the number of processors, but I forget if we have a talk later that involves the parallelism. There are definitely limitations to how much RMG can use parallel processes, but there are a few aspects where this can sometimes speed things up. All right, so for the most part, this talk is going to be about going through the RMG input files and how to read and write them and construct a mechanism that you are interested in. So one thing I want to hammer home, I've been an RMG user for about 5 years now, and I check the documentation pretty much every day. I go to the RMG website as well. It's really helpful for looking things up because it's a huge software package, and so that's where all of the answers are. So I always go there to look. So the GitHub page is really great for searching if you have questions. I would say mostly the documentation is the first place to look, and then if you want to go deeper, searching on the GitHub website is a really excellent tool. Okay. All right, so here is our sample RMG input file. It has different sections where you give it different information on things like the databases, the different species you want it to include, what kinds of reactors you want the gas to react in, or liquid or solid, the model, so that's how RMG is going to build parameters for how RMG should go about constructing the model, and then a whole bunch of extras that you can choose to use the defaults for or specify yourself, like simulator tolerances, species constraints, things you want to forbid or encourage, I guess mostly forbid, pressure dependence, and there's also machine learning thermoparameter estimation, and a few extra miscellaneous things. All right, so starting with the database, we talked about this, I think Richard mentioned it a little bit at the beginning. Just to want to reiterate, the way RMG generally works is if you give it a species that it has to estimate the thermo for, first thing it wants to do is check to make sure that if the value is in the library, because those tend to be, or are almost always higher accuracy. So it'll try to grab that, but if it's found something that it doesn't know and is not in the library, then it'll do some form of estimation. And so starting off with the database, the specifications here. So what you're telling RMG here is which libraries to use. So going back to our figure here, RMG in general, the database is huge. And if you were to load every single library that's in the database, it probably would not be very helpful because for any given mechanism, there are probably only a handful to a dozen of libraries that are going to be relevant to your chemistry and recent. There's been a lot of great work over the years of grad students adding stuff to the database, but inevitably people come up with better DFT methods, and so you want to be selective about what you include. All right, so the first option for our database, we can tell it which thermo libraries to include. Primary thermo library is a pretty standard one. I'll get into, there's a list of recommended libraries at the end that we can talk more about. But anyways, this is your list of which thermo libraries, the highly accurate ones to include. There's an equivalent one for reaction libraries for the kinetics. I'll show this at the end, but there's the list of recommended ones, but you can also go to the GitHub page to see what's available and look through there to see what's interesting. Seed mechanisms. So that's what you want the model to start out with. So we talked about the core and the edge. And so whatever you put in the seed mechanism, it uses the same type of file that you would pick for a reaction library. It's a set of reactions that automatically gets added into your core. A side note, anything you pick for the reaction libraries, that automatically gets added into the edge. So RMG will at least consider everything that is in a reaction library, or it's there available for it to consider. Kinetics depositories, that's a list of specific reaction kinetics that it can use to help fill out the estimation trees for estimating your reactions. The kinetics families, this is an interesting one. So that's all of the different templates and possibilities of how RMG can react with itself. Default is usually pretty good for gas mechanisms. There are a few different sets of sort of these named words. So you can either provide a specific list of families like H abstraction, disproportionation, R addition multiple bond, and there are also sets of these that are defined in this. This is the path inside RMG database. It's in this families recommended.py has a big list of sort of named sets. So if you're doing like surface reaction chemistry, you probably want to include the surface families in addition to defaults. And then for kinetics estimator, rate rules is our only option. But I think at some point someone had an idea to probably do like machine learning or something different from rate rules. But at the moment, it's just rate rules for estimating kinetics. All right, so moving on to the next block, we've got our species descriptions. So Richard talked about different ways to describe those with your, you can use things like the INCHI or SMILES or an adjacency list. One option that we have here, the first thing is that if you list out a species in your input file, it automatically gets added into the model core. So this is actually another good thing to do to help make your models consistent. If you know that you're going to run, for example, a methane combustion mechanism multiple different times with different chemistries, it can be helpful to, if you know what are some of the primary most important species, like I'm always going to have methane, always oxygen. If you list these, then RMG will create them always in the same order, and so they'll always have the same name. And so when we go to the simulation, I'll show in the afternoon, that simplifies things a little bit. And so it can be a good idea to include just a good starting set of species just to make your code writing easier later on. one other option we have, you can set reactive equal to false, and RMG will just not attempt to make any reactions using that species. So in this case, we've got nitrogen, and we basically say it's a bath gas, and so it's not gonna be reacting with oxygen to form something else. But I will mention RMG can handle nitrogen chemistry. There are many nitrogen libraries people are working on adding thermochemistry and kinetics based on nitrogen, but in this example, it's not going to react. All right. So just another plug for the RMG molecule search on the website. I use it like every day. It's just very helpful. Okay, so moving on, we've specified our databases. We've listed some of the species that we'll start out with. So the next step is to add which reactors RMG is going to include. And so you have to specify at least one reactor, because that's what RMG is doing, is it's reacting things to figure out what should go in the mechanism. But you can specify more than one. So we'll just start off, the simple reactor is one of the built-in RMG reactors, and so you can give it the initial conditions, so that'll be a temperature, a pressure, and your initial mole fractions. So you remember or from a previous slide, we defined our nitrogen, oxygen, and ethane. You can describe a lot more species, like, maybe there's also methane and OH and water, and you don't have to include them in the initial mole fractions. They'll just be set as 0, but they're still included in your model. Okay, so these are the required inputs for your simple reactor. You also need at least one termination criteria. So we talked a little bit about that earlier. The way termination criteria work is that there are a couple different ways to specify them, which, sorry, I forgot that. I think I have a slide on it a little bit later, so I'll get more into detail there, but they work as sort of this condition or the other condition. So whichever condition is reached first, that'll be the end of it. So the three options that we have here, there's termination conversion. So you can wait until 99% of your ethane is reacted away. That's this termination conversion here. Termination time is just a time on how long the simulation runs. So if you can run for that long without finding new species to add, then we decide that that's done. And then termination rate ratio is where you look at the we'll talk about this, the characteristic flux. So when you do your reaction, at some point a lot of chemistry is happening, and then presumably at some point it reaches sort of a steady state. And so you've got that ratio of what was the most active chemistry compared to where you are now. And if you get to a point where the ratio is big enough that, or I guess small enough that nothing is happening anymore, then it considers that to be done. Okay, so you also have the option of making ranged reactors, which you'll notice it's the same syntax as a simple reactor, but now you've got a range of temperatures and pressures and mole fractions. And you just tell it the range, and then you tell it the number of simulations to do, and it sort of spaces out along that I guess multi-dimensional grid of conditions and runs reactions at those conditions. One other thing, you can provide balanced species is one option. If you give it a range of initial mole fractions, what it'll do, if you don't specify balanced species, is it will normalize it. So it'll start off with 72% nitrogen, 18% oxygen, and 5% ethane, and that doesn't add to 100, and so it just sums them and then divides by that sum to normalize and get something that does sum to 1. But if you use balanced species, then it'll keep the ratio of the other things the same, sorry, the oxygen and ethane the same, and it'll instead change the level of nitrogen to meet the balance there. All right, so we've also got, this is not an exhaustive list of all the reactors that RMG can do. There have been quite a few added, specifically using the reaction mechanism simulator, RMS. I believe this is one of them, the liquid reactor. So for this one, you specify the temperature and initial concentrations of your species. You can also specify constant species, which would be a list of ones that you want to have a constant concentration. You can also give it, you have to specify the solvent that you're using for your liquid reactor. And RMG has a database, and so you can basically use a keyword. You can look up the different solvents on the website here, and I checked, there are more than 200 in the database, so people have been working hard getting those solvent corrections in. Okay, so yeah, here was my slide on termination criteria. I guess just one final thing to add, termination time, I guess, can be a good choice if your species contains lots of radicals. The trouble with using termination time by itself is that you don't always know how long your reaction is going to take, and so sometimes you do want to combine these two. Okay. So now we're moving on to model and simulation parameters. So these are specific to the RMG algorithm for adding in new species. So tolerance move to core. I've mentioned, I should have had a picture for this, but the characteristic flux. At any moment during the simulation, the different species, the different intermediates are reacting and forming other things. And so RMG forms you can calculate the characteristic flux at any given time by summing up all of the different fluxes of which species are being added. I forget if it's an average. I should have looked up the equation beforehand, but it's characterizing how much how active the reactor is at that moment. And so if RMG is trying to figure out what it needs to add, there's this tolerance parameter. So if you're within some threshold of maybe 10% of, that's the default value, 10% of that characteristic flux, then RMG will be, aha, this is an important species. We should probably include it. There's also an equivalent tolerance keep an edge. This one's actually used for pruning. So usually as you're building the edge, RMG will come up with more species to add, and it'll just keep adding stuff to the edge. But sometimes the edge gets huge, and you wanna just delete stuff from the edge that you know you're never going to use. And so this is the tolerance to keep something in the edge. So if it's trying to do some pruning and the species never gets above that level, it's allowed to prune the edge species out. We've also got tolerance interrupt simulation. So this is very similar to the tolerance move to core parameter in that RMG, as it's running its simulation and it's making more of a species, if it gets above the threshold, RMG can realize, oh, I should add this species, but it doesn't necessarily have to stop its simulation. It could keep going with that simulation and try to find more species in that same iteration to add. And so if you keep this, usually we keep this the same as the tolerance move to core, but if you made it higher, then you could potentially find multiple species in the same iteration. One thing is that you have to, if you're doing pruning, we usually set this to be arbitrarily high so that RMG will not prune things unless it gets to the end of the simulation, because it wants to be absolutely sure that that species is never used before getting rid of it.
Sebi, what does that number 1e to the 8 mean?
That
Tolerance interrupt simulation?
Yes, so that's that arbitrarily high value for interrupting the simulation. So if we're doing pruning, then tolerance interrupt simulation. Yes, if we're doing pruning, then we want the tolerance to be really high, because if it's low, RMG will find a new species. It'll get enough of something new that it'll be like, oh, we got to stop, we got to add this. But it won't have reached the end of its time simulation. Sorry, I should move ahead to this is the illustration of instead of hand waving. You can see, you can imagine we're trying to do some pruning. We probably want to get rid of species C. If we have our tolerance interrupt simulation set at this level, RMG is going to run, and it's going to make enough of B that it's going to stop the simulation, be like, stop, we got to add B. except that it hasn't reached the end here, and so it doesn't have this part here. So it's like maybe we'll use C, and so it's not confident enough to be like we can definitely prune this out. Whereas if you set the tolerance interrupt really high, then it'll get to the end of the simulation and it'll remember that because B was higher than move to core, it'll be like, okay, I had to add B, but I also know that I never used C, and so I can get rid of it. Okay, I think there was one other. Oh yeah, so filter reactions. That's sort of one of a more advanced setting where you RMG will by default, as it tries to react things together according to the templates, it'll come up with a lot of different species options. And so filter reactions uses, I think, the collision rate limit to filter out if things have a really low reaction rate, even like at their most reactive, if it's just not going to react at a fast enough rate, then it won't even generate those species and try to estimate their reaction rates. Okay, and then after the model, there's also the simulator tolerances block where you can specify the absolute tolerance and the relative tolerance. There's also a tolerance for doing sensitivity analysis, which I will say is that should probably be removed because I think we now do most of our sensitivity, or we encourage people to use RMS for the sensitivity. But we'll talk more about the simulator tolerances in the afternoon session with the simulator. All right, so yeah, I talked about this a little bit, but this is a sort of example iteration, a single iteration where RMG is running a simulation and trying to figure out which species it should add. So there's this tolerance of move to core. So as it makes A, it will, once it gets above this threshold, it knows that it should add A. And if we're not doing pruning, usually we set the tolerance interrupt to be the same. And then as soon as it reaches that tolerance interrupt and tolerance move to core, then it knows to add A. It'll stop the simulation there, restart it with A, and then go again. Okay.
One question from Zoom is if the question, what's the recommended tolerance for edge species and core reactions? And is it the default? Or the default tolerance is?
Yeah, I think it's a default. I want to say it's like 0.01 tolerance keep an edge. Oh, sorry, did I get at the wrong
I think his question is, what are like the absolute numbers, the recommended tolerances? And then kind of my question is, are those defaults normally good, or do you normally need to adjust these tolerances?
So
in your experience,
correct me if I'm wrong. I think the tolerances are relative to the characteristic flux. So it's not an absolute number of like moles per second. It's seeing what the reaction is making, and that sort of sets the baseline, and then the tolerance is just 10% of that. As for whether the default values are good enough, I would go back to I think Richard's advice in the first session was you maybe want to start generating sort of a smaller model, and then you can, once you think you have the main parameters reasonably well calculated or estimated, then you can, if you decrease your tolerance, sorry, I want my picture. If you wait for it to settle. If you decrease this tolerance, you're going to get more species to keep adding in. And so you can run RMG multiple times and keep decreasing that tolerance to try to get more things into your model. And what you will probably find is that it'll converge at some point, and adding more species, lowering this tolerance doesn't help you at all because you've already gotten all the critical chemistry in there. Oh.
I think we'll hear more from Matt Johnson this afternoon with tips on that kind of thing.
I had a question on how RMG works. So you start with certain species in the core, then based on the reaction schemes or templates, it generates all possible reactions of these core species. And then it simulates the reactor. And if one of these if the tolerance interrupt simulation is hit, for example, before you've reached the target conversion or whatever termination criterion you use, it'll add all species it found relevant to the core and then restart the simulation from the start.
Yes.
Okay.
that's my understanding of it. Actually, I'm going to pause the slideshow here and jump to, I think this is maybe, it's a similar but probably more helpful illustration of how RMG is working. So I'll go over this at the end, but one of the, if you ran your super minimal example, one of the outputs that RMG gives you, if you have it turned on, is the solver results. It will plot what sort of the equivalent of that simulation I was showing earlier. So just to give you an idea, the numbering scheme here, one is the one is consistent down these images. That's the reactor number, and then the 6, 7, 8 is how many species are. I think that's added into the edge is why. So it starts with 6, but there's only 2. So for the very first simulation, it doesn't get anywhere, or like it immediately is like, oh, I got to add all these species. So you can see that you don't see anything because the time scale is so small. So as I keep iterating, so that's 7, there's 8. Now it's starting to add species. It gets all the way to 1 millisecond before it finds something else. This time, you'll notice it restarted. It didn't get as far this time before. When you change the starting composition, it might run for an even shorter time than the last time. So it's not like it always gets a little bit farther in the simulation. It changes every single time. Adds another species, adds another, and then finally you start to get things reacting. And so that's where the super minimal example ends, because then you finally get enough of the conversion going. Okay, let's get the simulation or the presentation going. Oh no, let's go back to the.
While Sebby's pulling that up, there's a question on Zoom. If I have, just to get this right, the tolerance can be time-based. If I have A plus B plus C and want to start with A plus B and add C after some time, is that how we set the tolerance?
I don't think that, or the tolerance, or the tolerance I don't think changes, but the characteristic flux might. I think is that.
I don't think you can introduce C into the simulation after some simulation time. You couldn't have it's like A and B have been reacting and then C gets added. I don't think we could set that up. We could say you start the simulation with A, B, and C all there. So I think I've misunderstood the question, unless that's the answer. Ask some more details if we haven't answered it.
All right, so I think we're almost through our blocks of the input file. So now we're on the miscellaneous ones. So generate seed each iteration will save out everything that is in, or I'm sorry, this one is, it will set a save point every single time of all the species that are in the core and edge, so that if your RMG run crashes, you can then restart from that seed mechanism after the fact. There's save simulation profiles, which saves the concentration profiles every single time. I will say in general, the things that are in here will slow RMG's run down. And so if you want to run really fast, you probably want to set most of these to false. But if you want to if you want some really good tools for diagnosing things, I'll show you what each of these actually gets you. So generate output each HTML. This is another very slow one. I would say the save edge species is the slowest, because that saves at every iteration, it saves a copy of everything that's in the edge. And as we've mentioned earlier, the edge can get really large, so that can take a long time to write to disk. This generate output HTML saves a summary report of all the species and reactions that are in your mechanism. And it's a nice report to click through. And then verbose comments, I shouldn't have even mentioned this. There's like a very, very small subset of when you would want this to be true, because it tells you how the kinetic rate rules are averaged, and these can get ridiculously long and just clog up your RMG log file. All right, so there's a few other specialty blocks that you can add. So pressure dependence is one of them. So usually, or under many combustion circumstances, our reaction rates only depend on temperature, but there are other cases where they also depend on the pressure, and this is usually for small molecules at high temperatures or very low pressures. We've got I'd say the modified strong collision is the recommended way. I think we've got an entire talk on pressure dependence, so I'll try not to say anything wrong. And these are usually parameterized by Chebyshev or p-log rates, and I think that's all I'm going to say on pressure dependence. Oh, sorry.
If we don't specify that pressure dependence block, then no pressure dependence will be generated by default.
By default, I think you could potentially, like, if you included a library that had pressure dependent rates already in there, it might use them, but it wouldn't build on the network, or it wouldn't use them to like expand a pressure dependent network. Sorry, I think the answer is just no. RMG will not do pressure dependence if you don't include this block.
That specifically means like third body and follow-up reactions. I mean, if you
Oh.
increase the overall pressure, you're increasing the partial pressures as you're increasing rates as well. So that dependence is always there, just this mass action, element reactions. We're talking about third body reactions, whether it's a third collider or something like that, follow-up reactions stuff, which is more complicated to get right. Normally, it only happens at low pressure. So if you're operating at low pressures, then the pressure dependence is more real. Otherwise, we assume everything will have pressure.
What pressure is low?
It depends. Okay. All right, so species constraint, I would say this is a very useful block, though it can take a little bit of thinking to get right. So the basic idea here is that RMG can automatically generate a lot of things, but sometimes it doesn't make sense to generate all of those things. So for example, if I'm doing a methane combustion, I don't necessarily want RMG to come up with a very, very long string of alkane chains or things that I just with my intuition know it's not supposed to form. Or I'd say an example that I've seen more often with the surface catalysis mechanisms. One of the options here, so you can specify the maximum number of carbon atoms that you would consider in a molecule. You can also do the maximum number of surface sites. So if I've got some species that's adsorbing onto the surface, from our experience, these tend to not, they only attach at like 1 or 2 sites. So you'd only have like monodentate or bidentate species. You tend not to have the entire chain of the molecule just like being added on to a surface and connected that way. That tends not to happen in surface catalysis. And so rather than having RMG waste all its time by generating all these species that have very long chains of things that you don't think are going to exist, you set these maximum values, or I think they all have, I think, fairly reasonable defaults. And so you can think about the chemistry that you're dealing with, and sometimes you can come up with smaller numbers. So for example, for my surface reactions, this six oxygens, I would probably limit for the models I've been working with. I've never seen anything above 2, for example. One important caveat, though, if you're using these species constraints, is that you usually want to include this allowed section in case one of your input species or something in the reaction libraries, if they violate that, any of those species constraints, then you need to sort of artificially allow it, or else RMG will say, oh, this is forbidden, but it's in my model already, and it'll just crash. So you do have to add these in. Let's see, a couple of sensible defaults. It depends on the chemistry, but usually 2 radicals is a good limit. Although Yenting pointed out the nitrogen triradical. Let's see. And then, yeah, maximum surface sites usually limit to 2. I'll just mention very briefly, there's a quantum mechanic QMTP. This is the sort of on-the-fly quantum chemistry calculations that has, it's a sort of legacy part of RMG, where it can estimate thermochemistry that is I think it used to be more accurate than the groups, but the groups have since been updated with a lot of extra data, and so it's usually better to just use the groups. And I don't think anyone is currently working on this, but I do think it still exists in the RMG code. There was a paper in 2019 that they built a machine learning estimator for species thermo. So this uses graph convolution neural networks, and this was trained on a large number of cyclic and polycyclic hydrocarbons and their oxygenates. And so I would say if your system uses a lot of these kinds of molecules, it's probably worth using it because it was trained on a whole bunch of data, and they showed that for at least this data set of that type of molecule, it was better than group additivity. But I would say if you're dealing with like sulfur or surface reactions or something, you probably just want to stick to the groups because they're a little more general purpose.
And I'll add for this that this has been removed in the latest versions of RMG just until we can update the Chemprop backend.
yeah.
So that's what I'm working on, and hopefully this year we'll have that added back in.
Mm-hmm. Yeah. Okay. So one other type of reactor, this is a bit newer, are the surface reactors. So RMG can handle surface reactions, catalysis mechanisms. So they talked a little bit earlier about how you would specify a species. So if you just have a single metal, platinum is the default in RMG, you use this label X. And then if you want to absorb something onto your surface, you can write out the adjacency list or use the star with the smiles. There's this catalyst properties block that you'll have to specify. In the past, you had to specify the binding energies for carbon, oxygen, nitrogen, and hydrogen on that surface. But now there's a database, and so you can just tell it which metal, and then the 111 is telling it it's on the 111 facet of the rhodium metal. All right, so for our surface reactor, it's very similar to the simple reactor. You specify your initial conditions, except this now has, you have to specify the initial surface coverages. So here, this is saying that everything is a vacant site. There's nothing absorbed on the surface, but you could change it and, specify, oh, we've actually got half of it's covered in oxygen. But you'd have to define the species and then add it here. And then you also have to define a surface volume ratio and then your termination criteria. Oh, are we? Oh, okay. I've still got 20 minutes. All right. Okay, so next we've got, this is sort of a list of which libraries you should include for your chemistries. I will just say briefly that it's very important if you want to get the model right, you want to have good libraries that are able to describe your reacting chemistry. Sometimes you want seed mechanisms for small molecule chemistry. In particular, if you're doing combustion, the H2 plus O2 chemistry, you really want to include that as a seed mechanism because it's really important. And if RMG doesn't find everything exactly, and it might not, it is just a way of making sure that you get that very important chemistry right. As for how you pick the libraries, there's kind of an art to it. That usually consists of asking the older members in your lab or your advisor which ones you should use. It's also it's kind of, you combine it with just searching through the literature, because all these libraries, they're based on someone did a study and published a paper, and then someone inputted that into RMG. So you can go, I think there will be a talk on this at some point about adding stuff to the database. If you're investigating something and you don't feel great about the chemistry, you can look online and maybe someone has published a mechanism that you can add to the database. So anyways, these are the ones recommended for oxidation. Like was mentioned earlier, the H2 plus O2 is very important for combustion. There's also, for these sources, I'll just mention the active thermochemical tables. And then you can see there's a couple that are done with different DFT methods. So you've got coupled cluster, the complete basis set with 1D hindered rotors. Let's see, yeah, this Klippenstein-Glarborg one comes up a lot. Let's see, I'm not going to spend a lot of time. Oh,
Just to add a couple of points if you go back. First point is that it takes them in order. So the first library it finds a species in, that one wins. So put the most accurate to smallest libraries first, probably like this. So the ones that you really trust come first in the list. The other thing worth noting is that the kinetics in a seed mechanism are often very dependent on the thermochemistry in that same model. So if you're using Klippenstein's seed mechanism for the small molecules, use Klippenstein's thermo for the small molecules, because that's the thermo he used when making the kinetics. And because all the reactions are reversible, it's very often important to keep them matched up. So when you're flipping your seed mechanisms around, double check your thermo libraries match and put things in the right order.
Mm-hmm. That's a very important point. Yes, thank you.
So
Oh, yeah.
to repeat the question, he's asking about the order. So the order that you specify things in your input file. Near the top of your input file, you say where to get the data from, which libraries to use, and so on. The order that you mention the libraries in there is the order that RMG will use for that simulation.
So I'll leave these slides for you can look up if you're dealing with nitrogen or sulfur for your system. I'll also mention again, you can go onto the RMG GitHub page and click through to the RMG database to see which libraries are available. And usually they've got some sort of metadata at the top that links you to the paper. So you can sort of get an idea of when and for what purpose the data was generated. All right, so finally, I think this is the last slide, which is talking about what RMG will generate. So I'll briefly talk through these slides, and then I'm going to show you some of the most important ones. So first off, RMG log is the primary log, where as RMG is running, it outputs what's going on. So it's a helpful diagnostic tool. If you have any kinetics that violate that are collision rate violators, it'll generate this file. And so you probably want to take a look and make sure that your rates don't exceed the collision limit. If you've selected the option to restart from seed, it'll save out the seed mechanism each time. It also generates the mechanism files and then a few extras. And at this point, it's more helpful to just show. So, all right. So now we're going to move over. I hope those of you using Docker will forgive me for using my. I've got Windows Subsystem Linux on my computer, and it's very easy to go between the files this way. So we've run our super minimal example using the Python rmg.py input file, and it's generated. I type ls to show what's in the folder here. Although I guess I could also go back here. These are the same. This is the same file. So when I run RMG, well, first off, we'll just take a look at the RMG .log. Let's see if I can open this in VS Code. Just to give you an idea of what this looks like. So it starts off, it tells you, I don't know. There we go. Okay. Yeah, so it's got a standard header. It tells you which precise git commit or save point it's using for RMG.py. RMG database reads out a copy of the input file. So this is the example where if I had multiple libraries, the first one is the highest priority, and it'll use that one. So yeah, it lists out the input file, loads the database. Sorry if I'm going too fast for the Zoom to keep up. And then it starts enlarging the model. And so you can see it'll say that it's created new species that it added to the core and to the edge. And it'll keep going on for a while. You can see it's starting to add species. I think Oh, the question is, why would it add helium? I think there are a couple of bath gases. I think helium, argon. I forget if these are part of the input file. I don't think they are. Yeah, they're not. Oh, they're probably in the primary thermal library. That might be it. I'm not sure. I don't know offhand, but yeah, you will, when you generate an RMG mechanism, you will end up with helium and argon in your model, I think, every single time. Let's see. Okay, so it runs RMG, adds things, and then you get to the very bottom, and it'll say model generation completed. Final model. It tells you how much is in the core and how much is in the edge. So this is a very small, super minimal, only has 13 species and 19 reactions. So then we can go back to our super minimal folder, and you can see sort of the more, I would say the most important result of RMG is the output. It gives you both the Chemkin file or the Chemkin format, also a Cantera format. I think you can also get an RMS format. I'm not sure if that one was generated here, but the Chemkin is the one I usually look at first. So chem annotated .inp. So that's a Chemkin format. Let's see. Open this guy. All right. So this is the contents of the Chemkin file are that's what RMG has put together. That's the output of RMG. And so the way this works is it first specifies all the elements that are in your mechanism, and then it tells you what your species are, and then it goes into very great detail about the thermodynamics of each of those species. And so this is kind of it's a really, I think, antiquated format where it's still like there's some legacy of like the column width that's like still traced back to like when there were punch cards or something. And so that's why things are like formatted in a column format. But basically these are the parameters that will give you your heat capacity, enthalpy, and entropy. The format is called a NASA polynomial. You don't have to dig into that level of detail, but that's what RMG uses for every single species. And then for every single reaction, it gives you the reaction rate. Usually this is in an Arrhenius parameter. So you've got your pre-exponential A factor, a temperature exponent, and then an activation energy, which the units of which I believe, oh wait, they were specified here, are in kcals per mole. So, and then in the exclamation points here, those are just comments. So they tell you that this, for example, this is a radical recombination reaction. You've got your two hydrogen radicals recombining to form molecular hydrogen, and it just happened to this exact reaction already exists as a training reaction for the family. So that's sort of a lucky guess where RMG has rather than a pure estimate, it's using one of the training reactions that was used to generate the reaction rates in the tree. Okay, so Chemkin file gives you a big list of all the reactions and species and sort of the numbers that are associated with them that you can use to get the species enthalpies and then the reaction rates. One other thing that RMG gets you that is very important and you don't generally doesn't get published with when people make models, they don't generally give you you have to construct this on your own, the species dictionaries. So we spent a lot of time talking about how to specify molecules because the structure of those species is really important to RMG to figure out isomorphism and to see if things are part of the same groups or reaction templates. And so it has to have a precise definition of every species for every species in your model. So usually for the input file, you can specify the SMILES, INCHI, or adjacency list, but as the output, RMG will get you every single adjacency list for every species. And so this file can get quite long, but it's also helpful for debugging. It's also very important later on, we'll show you some of the RMG tools that you can use for analysis. If you just want to run a simulation you don't necessarily need this information, but some of the more advanced RMG tools do require the species dictionary definition. It's also really important for comparing two different mechanisms to find differences in the species and the kinetics, because you want to make sure that you're comparing exactly the same species. And so if you got just sort of a label from someone published a mechanism and they called something butane, and then a different set of researchers published a different model that has it listed as CCCC as the smiles, this adjacency list is how you make sure that you're comparing apples to apples. All right, other important files. So that's the Chemkin version of it. There's also, I'll just show you briefly the Cantera version. So just as there is a Chemkin output, RMG also gives you a Cantera version, this cantera.yaml file, which has a lot of the same, or I should say, it has the same information as what's in the Chemkin file. The difference then is what's saved in the Cantera side of things doesn't require the species dictionary, but it's still got your list of elements, your list of species, and then these are just in YAML format. You've got the different, for example, NASA polynomials for your species, or for your reaction rates all the way down here at the bottom. You've got your rate constants parameterized as in your Arrhenius form, or a pressure-dependent Chebyshev form if you've got pressure dependence. Okay, almost through here. Let's see. Okay, so that was the Cantera side. I'll just mention, if your RMG model does not finish all the way through, it doesn't generate the Cantera one. It does that at the very end, but you can, there's a script for converting, which is in the input or the example file that I'll show in the afternoon. We can also look at, I mentioned there's the seed mechanism. So as it, in this example, we told it to save out the seed mechanism every time, so you can restart it if it crashes partway through. And so you can look at what it saves is basically a Chemkin file every single time. And so if you wanted to restart it, it's already got all of the species. Oh, this is rather not a Chemkin format. This is RMG's internal library format. So each entry, it tells you what the reaction rate is. So it's a little bit different from the Chemkin format. This is what RMG, how RMG stores things in its own database, but it's very similar. It's a very similar set of information. And then it also has the dictionary that specifies the species connectivities. Okay. Oh, this is a good one. This is the HTML report that you get when you run RMG and select the option to generate the HTML report. One downside I will mention, it doesn't just slow your RMG run down. It also, in order to get you the pictures of the species, it will generate, well, pictures of the species. And if your model, if you're saving the edge and you're generating a really big combustion model, this can get huge. And I think this is part of the reason we've been hitting our inode limit on our computer cluster, I think in part because if you don't turn off that image generation, it makes a lot of files.
If you have it on the edge.
Mm.
Like I only turn this on for the edge if I'm trying to debug something really weird. But I almost always have it on for the core. Useful.
So yeah, we can look through the report and it'll show us our species thermodynamics. So you've got your enthalpy, entropy, and then heat of formation at different temperatures for all these different species that are in our model. And it will also tell you about the reactions that are in there. Let's say I want to show these details, so I will check these boxes. It tells you how many came from each family. So most of these are H abstractions, but there's several reactions involving radicals. So here again, it'll show you the pictures, which can sometimes be a little bit easier to read or visualize than the text equivalent. You can also zoom in. There are often comments that are saved associated with each of the reactions and species that will sort of give you a trace of where they came from in the RMG database. And this is a project I'm working on related to estimating uncertainties, where the idea is that just from that comment, you should be able to reconstruct exactly where and how RMG made its estimate, so that you can have some idea of whether it was a good estimate or a bad estimate. All right. I think that's, yeah, we talked about the solver, so that showed the iterations. Species has the, oh, there's one other in the, I'll just mention real quick, inside the Kempkin folder. If you're doing, this is important for flame speeds. There's this transport data file that if you run your model all the way to completion, it'll get added into the Cantera file. But if you have to automatically generate, or sorry, manually generate your Cantera file from the Kempkin one, then you also have to include the transport file. So just letting you know of its existence if transport is important to your system. With that, I think that's everything that I wanted to cover about how to run RMG in general. So if there are any questions, I think we've got a couple of minutes.
Yeah, thanks for the nice introduction. So just to clarify, the reactor, which you mentioned quite at the beginning of the talk, has nothing to do with the classical or boundary cases of reactors in chemical engineering, like plug flow tubular reactor, continuous direct tank reactor. It's more or less defining a space where some reactions can happen, or?
So to make sure I understand your question, you're asking, or can I rephrase your question as what can you this reactor is in terms of like how it would relate to like plug flow reactors? Or yeah, I'm pretty sure that the simple reactor is a batch reactor with constant pressure. I think that's the, yeah, constant pressure and temperature. And so it's a really simple case where it can just sort of get everything reacting and see what it makes. But we'll get to, in the afternoon session, some of the different kinds of reactors that you can then go on to simulate.
Yeah, perfect, thanks. And maybe if you're also covering it in the afternoon or on Friday. So if I have some good physical parameters not yet included in the RMG, I can probably also insert it. Or is it not possible to insert my own data?
Oh yeah, you can add your own libraries. That's probably the way that I would go about doing it. You'll have to put it into the format that I showed here for the seed mechanism. But there are scripts to help you do that. Yeah, I think we'll talk about that.
So I'm curious how RMG handle when you have a range of pressure, temperature, and composition, initial composition. So is it like create a multi-dimensional grid and run a simulation on each point in that grid, and what is the how the output will look different? Like is it output a single network that would just operate in all of those grid points, or something else?
Yes, I think that's what it does. Is it? I don't know offhand what the output, how it describes the output. I know if you put multiple reactors, then you end up where's the RMG log file? All right, here. Yeah, well, this won't show it, but if you have multiple reactors, then it'll show. Sorry, there's a point where it says that it's reacting things together that I'm looking for. Conducting simulation of reaction system 1. So if you put different reactor blocks, then it'll get you multiple reactor systems. But I'm pretty sure for the ranged one, that counts as a single system. And so it'll do what you said, where it makes the multi-dimensional grid of the different conditions. And then when you specify the number of simulations or the number of grid points, that many they all have to reach the termination criteria. So it'll sort of sum together all the different reactions and species that it finds. And you might find more if you're going over a different range of temperatures and stuff.
I see. Thanks. And another question, I think it's about like how RMG, do value judgment when it comes to different kinetic rates or thermochemical data. Like, is it like the first data that it encounter when we specify the library, or like when they actually compare between values inside different libraries and which one is a little better than the other ones? Does it do that? And also, early in the morning, we say that if there's something that's not like a reaction in the template does not exist in the library, it will try to estimate. So does that estimation happen automatically, or there's some sort of turn on and turn off mechanism that we can regulate that?
Yeah, so it always checks first in the order of the libraries that you listed for the value, the kinetic rate. But if it can't find it, then it will always go to the decision tree. And I think there's a talk later about how exactly RMG estimates the thermo and the kinetics, but it has to come up with a number for everything. And so if it doesn't have a library, it always goes to an estimate. Oh, any on the, sorry, I've not been checking the chat. Okay. Yeah, if anyone has questions. Question about where, wait, that's, I think Jackson answered that one about, actually that's yeah, so I want to expand on this question of where are your files if you installed things in Docker. So this is one of the reasons I personally, I really prefer the Windows subsystem Linux, because I can just go to my file explorer over here, or if I can pull it up. Apparently I can't if I've got the chat open. It's okay, yeah. And if I scroll down, I've got this little penguin guy. I've got my files, they're all right here in my home folder. And I can, using the file explorer, it's very easy to just navigate through there. Whereas with the Docker, because we did the binding, let's see, I think you can add extra swap space.
On the bind mouse. It was when you launch the Docker, you have to say where to make the thing appear to be.
Yeah, one of these. Okay, so this is my personal Docker. So if I go to RMG Pi, I think there's a file in here. Yeah, my RMG files here. So I can go. I don't actually have anything in here. I can copy, for example, I don't know why I'd want to, but my I can copy the rmg.py file there, and then can, for the Docker in C, users, me, and then the binding I created here it is, my RMG files. So I can copy between here, but you still have to use, as far as I am aware, I don't know of actually that's not true. I do know of an easier way to move files around. But usually, yeah, you have to use sort of a combination of command line tools where you copy and move things into the sort of shared space between the windows and the Docker. One workaround that I found is that if you have a Jupyter notebook running, and we'll do this later today, although I think I think this is for my oh no, it's here. Okay, so I could it's not that much easier, but you could rename things. You could you can kind of you have a little bit of a GUI with the Jupyter notebook, so there's maybe a little bit more.
If you do the mount when you're launching the Docker, if you do the -v thing to do the mount, then it's kind of like your Windows subsystem. It still shows up the folder. It depends. You have the option of mounting any folder to any folder on the inside, and so you could mount it so that you can see everything.
Oh, just mount it to
Yeah.
the root?
Yeah, so
Oh, okay.
with a whole folder. So you can play around with that -v tag when you're launching the Docker, and then files on the outside of Docker are accessible on the inside of Docker and vice versa.
Mhm.
Um,
Yeah. I will say the other answer to where are my files, it's a little bit of a learning curve figuring out where to find, for example, the examples on RMG Pi. This is why I really like the searching the GitHub page, because you can maybe I want to find an ethane oxidation example. Here it'll show me, oh, it's inside examples RMG ethane oxidation. So that's a useful tool for looking up keywords inside RMG if you're looking for something in particular. Any other questions? I think we're over time, so I don't want to. Maybe we break for lunch now.
What was the degeneracy in the reaction specifically?
Because
Because I saw 0.5.
Yeah, I don't know why something would have a degeneracy of 0.5. It's supposed to be, as far as I understand it, the number of different ways that a reaction could occur. So like if you've got, if something is if you've got ethane with the two like methyl groups, if something is plucking a hydrogen off of there are many different sites at which, you can rotate the molecule and do that same sort of like H abstraction reaction. So I don't know where the 1/2 comes from.
But shouldn't this information usually be in the rate coefficient itself?
I think that's to do with the trees, that because the way the decision trees work, it doesn't necessarily know the degeneracy, and so it's relying on, this is just my guess, that the way the decision trees were trained, that's sort of an.
Yeah, I think if it was in a reaction library where we're saying someone has just said this is the rate of methane, we use it as is. If it's coming from a family, we're doing it per H atom or something. So we would store the value divided by 4, and then when we get it back, we'd multiply by 4. So we would end up with it right. But if it comes from the library, it's divided by the degeneracy when we were training the estimation algorithm. So when we use the estimation algorithm, we multiply by the degeneracy again to get it back. So I think that's why it can be confusing when it shows up and when it doesn't.